All right, so moving on with chapter 14, 14.6, charge motions in metals. So we've talked about charge in insulators, and now we're going to move on to conductors. So remember, these are materials where electrons can move freely. So in metals, the moving charges are electrons. We will talk about something called hole current, where you can have the positive charges that are moving, and then in ionic solutions it can be negative and positive charges that are moving, but for metals it's only electrons. So for this we need to go back to our thought model about matter from Physics 1. So this is our ball spring model. So we've got all of these vibrating springs together if we're going to do a more perfect model, then we've got the lattice. And so we have these electrons that are bopping around throughout this lattice. So most of the atom is in this lattice, and then we'll have just, say, typically an electron per atom that's bopping around. And these are called the sea, the electron sea. Sea of moving charges. And so these are bound to the metal, but not the individual atoms. So it's not like you just have a bunch of electrons that tip off of metal. They're going to stay within the metal, but they're not bound to the atoms anymore. And what we have, so you'll have the positive cores that are left from all the atoms that have lost their electrons, and then you've got these electrons moving around. And so like this. And so the electrons are going to be attracted to the protons, but they're going to be repulsed by the electrons. So we've got attraction and repulsion. And these are going to balance each other out. And we model this electron sea like an ideal gas. Now, we'll often talk about it flowing like water. However, that's not exactly how it works. So really, when we talk about the electron speed, we're going to talk about it like they're just kind of bopping around in a straight line like this. In reality, they're getting attracted to a proton, accelerating, and then deaccelerating, and then maybe repulsed by something else, and they're kind of moving around like this. So this is actual electron motion. And then this is the average velocity, or average speed, v bar. So this reflects the collisions throughout the metal. And this model is called the Drude model. And we're going to see this over and over again. So I want you to keep both things in mind, both this average speed and then what's actually happening. So And the electrons crashing around are going to cause some physical effects. So thinking back to that ball spring model of matter, so if something were to crash into this, we would expect that it would start vibrating up and down. And when it vibrates up and down, these springs are going to be moving back and forth, increasing their energy, and they're going to get hot. So we get an increase of thermal energy from increased vibrations. So if you've ever noticed that wires get hot, that's why you are actually feeling the effects of the electrons bopping around inside of the wire, causing the atoms to vibrate. Okay, so let's look a little bit more at this drift speed. That's that V bar, and how electrons move through materials. So, the average speed that an electron goes through a metal is called drift speed. And that's that V bar. And there are more complicated models of electron mobility, but this is good enough for physics too. And really good enough for a lot of calculations. So your circuit equations, if you're taking a physics-based test, are going to use this, come from the V bar drift speed. So it's good enough, but we've done very powerful physics with it. All right, so we're going to use the momentum principle to analyze drift speed. So we have dp dt is equal to the net force. So the change in momentum with respect to time is equal to the net force. Remember, we can write this in terms of delta. So the change in momentum is equal to the net force times the change in time, just simple algebraic rearrangement. And if you recall, for the net force in the case of a charged particle in a field, which is what's happening inside this conductor, so we've got our E times E net. E net would be the charge of the electron. So therefore, delta P is equal to E times the net field times delta T. And just a quick aside, what is this delta T, you might ask? Delta T is the time between collisions, because the collisions are what are accelerating these electrons around. I mean, we're really into crashing things in physics. And we're going to assume that the momentum of the electron is 0 during the collision, so it comes to a full stop. And thus, delta P is equal to P minus 0 is equal to E net delta T. So, and we're also making another assumption that we will show later is reasonable. So this is non-relativistic. And the answer for why we can assume this comes in chapter 18. So be curious and know that it's coming. All right, so continuing on with this derivation. By the way, derivations like this can get you out of a bind if you're ever taking an exam not just in my class, but a standardized exam as well, and you need to figure something out. So the velocity is equal to the momentum divided by the mass of the electron. Thus, the velocity, we have an equation for momentum. So P is equal to E times E net delta T. So velocity is equal to E times the net electric field delta T divided by the mass of the electron. Okay, so remember, we're after the average, V bar, not just V. So we need to think about the average delta T. So that's going to be, this is going to be the same, this is the same, this is the same, this changes. And this is what's going to drive that average. So we need delta T bar. So V bar is equal to E net times delta T bar over the mass of the electron. So we need to think about what physical factors impacts delta T bar. So and if you think about it, so if the metal is cooler, then it's going to be vibrating slower. That has an impact. So temperature can affect it. We can also see from looking at this that there is a relationship between the average velocity and the electric field. You make the electric field bigger, the average velocity goes up. So we can see all of the different influences that would impact electron speed through a given metal. Now, there is something called electron mobility factor. So U is electron mobility, and that's how easily electrons will move through a given material. And so V bar is equal to U E net, and U is equal to E over ME delta T bar. And I want you to prove this to yourself on your own. So now we've got V bar in terms of the electron mobility constant, and we've got an expression for the electron mobility constant in terms of the equations that are specific to a given metal. All right, so moving on, thinking about what it means when a metal becomes polarized. So metals can become polarized to, it happens relatively quickly, but it's a different type of polarization. So, and what we have here is a separation of charges, but instead of the atoms becoming little dipoles, we have something else. So essentially the electrons go to one side and our little protons are on the other side. And the convention is to do positives in red and negatives in blue. And so when this happens, you have the field from being polarized, which is going in that direction towards the negative charges. And then you have the applied electric field, which has driven the positive charges to that end, and then the net electric field is equal to 0. So when a metal is polarized, the net electric field is equal to 0, and it's a result of the polarized field, which is going in the opposite direction of the applied field, equaling each other out. And something to note polarized and charged are not synonyms. So something can be polarized and charged, or it can just be polarized. These are different concepts. So charged has to do with having an excess of either positive or negative charge. Polarized has to do with the separation of charges. So if we were to have excess electrons on this metal, you could still polarize it. You would just have it would be charged, and you could still polarize it by separating the two charges on either end. So a few notes. So the net electric field in a metal equals 0 at equilibrium. And what you have there is that the net field is equal to the applied field plus the field from polarization, which is equal to 0. This will be important in later chapters. The electric field is not always 0 in a metal. And we will see this when we study circuits. And when we study circuits, we really work on understanding the physics of what's happening, not just the equations, because you will see that the equations come from some really interesting assumptions. And then whenever you have excess charge on a metal, it's always found on the surface. So excess charge on a metal is always at the surface. All right, so we will stop here, and the next online lecture will be an example with all of these concepts.